Let's go a little deeper into Newton's third law. We've talked about the first law, that an object in motion stays in motion. We talked about the second law, that the net force equals mass times acceleration. Now a little bit about the third law. When two objects interact, they will exert equal and opposite forces on them. These two puppies, A and B, are having a little tug of war. A is exerting a force on B. B is exerting a force on A, and those forces are equal. Even if one of the puppies is losing, those forces are equal. One force you would call the action force. From puppy A's perspective, the force that puppy A exerts is the action force, and the force that puppy B tugs back with is the reaction force. These two forces are third law pairs, force of A on B and the force of puppy B on puppy A. Let's look at it with a bowling ball hitting a pin. Now the bowling ball is going fast and it strikes the pin. What are the forces involved here? There's a bowling ball pushing on the pin. That's the action force if you're the bowling ball. In which case, what's the reaction force? It's simply the pin pushing back on the bowling ball. That's it. But there may be more than one action-reaction force going on. This funny-looking guy pushing a rock has a force of the ground on him and him on the ground. And that's kind of important because he needs that in order to apply force to the rock. And then there's the force of the man pushing the rock. That's the action force, and the force of the rock pushing the man is the reaction force. We've said the action forces are the forces this guy is applying to things, those things being the ground and the rock. And the reaction forces are, in turn, those things acting back on him. Judging from the size of that rock, I'm going to guess nothing's really moving. So if this guy is caught in the middle, poor guy, I think there are a lot of third law action-reaction forces that we can identify, and they come in pairs. So you have the tractor, you have the elephant, and you have this boy hanging on by two ropes to either of them. What are the action-reaction pairs that you see? I'll just scribble them down as I think through this. There's the tractor, there's the boy, there's the elephant. I'm not going to worry about the ropes. And the reason why is, if he was holding onto the tractor with no rope at all, it really wouldn't change anything. So the rope is just kind of there for illustrative purposes. But you could eliminate the rope and just have him grab the bar of the tractor, and the same thing will happen. There's the tractor on the boy. I'll just go tractor boy, because tractor on the boy and boy on the tractor, right? And there's the elephant and the boy. So you have the elephant's force on the boy and the boy's force on the elephant. You typically don't even indicate which one's the action, which one's the reaction force, because they are equal and opposite pairs. One of them doesn't have the seat of honor in this picture. A tractor wouldn't be able to move forward if there weren't friction between its wheels and the ground. That's how forward motion happens. So there's a force between the tractor and the ground. Happens to be facilitated by friction. But those are the agents that are applying the force, the tractor in the ground. Not to mention the elephant in the ground. So we have four pairs of forces. Tractor on boy, boy on tractor, elephant on boy, boy on elephant, tractor on ground, ground on tractor, elephant on ground, ground on elephant. And those are called third law pairs. So now let's look at a case where we have rope tied to a wall and a scale on there. And we'll look at the various forces that are acting on various things here. So I have this scale in between. Let me explain how this works. You have the kid holding a rope, and the rope is tied to the scale, maybe attached to a hook behind the scale. And then on the other side of the spring scale is the end of the second rope, and it goes to the wall. And so when you pull on this rope, that spring scale reads how much force you're pulling with. So the question is now, if I replace the wall with this very stubborn elephant who's going to pull back and refuse to let this kid lead him to the circus tent, what does this scale read? Does it read 500 newtons? The kid pulls just as hard. The boy pulls with 500 newtons in either case. So what does the scale read when the elephant is putting up a fuss and refusing to get dragged along? Why don't you stop for a minute and think about it. Pause the video if you need to. Okay, did you pause the video? So what does the scale read? Do you think it reads 500 newtons? It does. It reads 500 newtons. How is it any different than the top picture? The rope is tied to an elephant. Yeah, the elephant's pulling back with 500 newtons, so you might think, oh, there must be 1,000 newtons reading on that scale. But how is the elephant different from the wall? The elephant's refusing to move. The wall is refusing to move. So you get 500 newtons in both cases. A similar argument is looked at here. You've got this weight hanging over a pulley and attached to a pole in part A. But in part B, that rope is hanging over a pulley and then draping over another pulley and going to an equal weight hanging on the other side. In which case is there more tension in that rope? Remember, tension is the force that pulls on the weight. You know, remember if we did a second law free body diagram, we would have the force of gravity of that weight going down, and we have the force of tension going up. And if the weight doesn't go anywhere, which it clearly doesn't, those are equal and opposite. So in A or B, do you have more tension in the rope? In B, you have this rope being pulled on by both weights on the left side and the right side. Whereas in A, it's just being pulled on by the weight on the right side and is tied down on the left side. Which rope has more tension? Think about it for a minute. Pause if you need to. If you look at the right weight, you have the force of gravity pulling down. And remember, force of gravity is just mass times little g. And you have tension pulling up. F sub t for tension. And over here on the left weight, we can do a free body diagram on it. Force of gravity going down, and you have the tension going up. Let me tell you something about tension in a rope. The tension is the same throughout a rope. Think of tension as a force that the rope contains. It applies that tension to whatever it's attached to, but think of the tension as a force contained inside of the rope. So everywhere throughout the rope, you have that tension. Meaning on the right end and on the left end, you have the same tension. So these two tensions are the same because they're attached to the same rope. The force of gravity is the same because these two objects have the same mass. In fact, I'll just label them as such. The tension is the same whether you have it this way or you put a pole there and tie that rope down and forget about that side. You have the exact same tension either way. So the answer to A and B is they're the same. I went through this with you once before, but I want to do it again because it illustrates the connection between the second and third law. So pause the video and think about this question. So you have this thing falling off of a truck, and it weighs a lot. And as it falls towards the ground, it accelerates at 9.8 meters per second squared. Does the Earth accelerate towards it? Because Newton's third law says that when two objects interact, they apply equal and opposite forces to each other. And if that object is falling to the ground, it is interacting with the Earth by gravity. So while that safe is falling, we would say that the safe and the Earth are interacting with each other through gravity. The Earth is feeling the same force as the safe. So what's its acceleration? F equals ma? Well, the Earth has much more m than the safe. They have the same ma, the Earth and the safe, but the Earth has more m, therefore it has less a. A lot less a. So little that nobody could ever measure that acceleration. But the fact is, it's not zero. It's zero followed by a lot of zeros and then a little number, but it's not zero. So let's look at the combination of second and third law in a single force diagram. The second and third laws tell you different things. Let's illustrate this with our prototypical situation of a box on a floor getting pushed. So let's do a free body diagram on the box. You have the normal force going up. You have gravity going down. We're pushing it. And there's a little bit of friction resisting the push. So you have this pushing force and this friction force. Pushing and friction are what are best referred to as second law forces. You add them up to get ma. The same goes for the gravitational force and the normal force. You add them together to get ma in the vertical direction. There's no motion at all in the vertical direction, so ma is most definitely equal to 0 in the vertical direction, which is why we can say that the force of gravity plus the normal force equals 0. What is important about a third law pair in this picture? Let's take another look at it. Let's look at the hand and the box. So the hand pushes on the box, and I'll label that force of the hand on the box. You know what that is? That's just the push force. That literally numerically is equal to F sub push, right? The force is applying force to the box. We call it F sub push. For the moment, I'm going to call it F sub hand on box, just to make a distinction here. The box pushes back, and we'll call that force of box on hand. So those are different things. These four forces are all related to Newton's second law because they are acting on the same object. These two forces are related to Newton's third law. They are an action-reaction pair. Notice they don't operate on the same object. One acts on the box, the other acts on the hand. So there's a difference between forces that are related to each other through the second law and forces that are related to each other through the third law. The second and third laws tell you different things. The third law puts forces in pairs and talks about an interaction between two objects. So you have the man pushing the rock. The man applies a force to the rock. The rock applies a force to the man. Those two forces are action-reaction pairs. The man applying force to the rock and the rock applying force back on the man. And they are equal forces, and they are in opposite directions. That's what characterizes a pair of forces that are arising due to Newton's third law. Each one of those pairs acts on a different object. One acts on the man, one acts on the rock. Each force comes from the same interaction, the pushing between the man and the rock. These two forces do not contribute to the net force together. The force of the man on the rock will contribute to the net force on the rock, and the force of the rock on the man will contribute to the net force on the man, but they don't get added together ever, those two forces. In the case of Newton's second law, you have forces that do go together to give you the net force. Let's look at the mass hanging from a rope. We look at two forces that seem to be acting on that mass. There's gravity pulling it down, and there's tension pulling it up. In the event that there's no acceleration, those two forces are also equal and opposite. But what's different about them and, say, the force between the man and the rock and the man, is that those two forces are both acting on the same object, the box that's being lifted. One is from the rope, the other is from gravity. So each force arises from a different interaction. Gravity is an interaction with the earth. The tension in the rope is an interaction between the box and whatever is doing the lifting, your hand, a crane, whatever. These two forces are summed together to give you ma, the mass times the acceleration, and that's Newton's second law. So that's two different ways of looking at what's usually pairs of forces. I say second law groups because there can be more forces involved, and so I shouldn't say pairs, I should say groups. There might be friction, there might be air resistance. You have to consider all of them and add them up. We've already done some examples where there are three forces that make a Newton's second law group. That hopefully clears up some subtlety between Newton's second law and third law. With Newton's second law, you can immediately jump to some calculations. Newton's third law helps to protect you from considering forces that aren't part of the net force, but have some physical meaning to them. You might be equipped now to do the Newton's third law assignments that I have posted for you to do, so give them a shot.